Hi, today is Tuesday, July 12th, 2022. It's pretty hot out today, so I apologize for the whoosh that you might hear in the background. It's my air conditioning. So I wanted to put together a video to go over some LCD material that is pretty extensive. So hopefully this video will help unpack some of the details. I did put together a thread, which there'll be a link in the description over to it, and this is an explanation of some of the LCD functions and some useful tidbits on what's going on. So that's out there if you want to take a look at that. And I also put together a zip file of this directory, which has got all the source code, header files, and all the things that are needed to reproduce your own LCD function test program like the one that I put out there. But let's go back and take a look at the quadrature signals. So this is what's coming out of the encoder. Those of you that have watched my videos know I've got a PCB out there that cleans up the Bourne's rotary encoder signals, and the switches are open, off, or closed on in the encoder, and there's two sets of switches, and they generate this classic quadrature signal. And the detents here marked with D are these vertical dashed lines, and the encoder kind of sits at these detents. And if you turn it slowly, you can kind of watch these individual events, but that's really not the idea. The idea is to go from detent to detent. When I started this project, I went with one interrupt service routine set for INT0 and INT1, which actually counted each detent as one. And it worked out okay, but since then I've discovered there's actually a better method to deal with this encoder as an input device, and it actually goes ahead and triggers on all four of these events. So you've got a level change here, which is 1, you got a level change here, which is 2, a level change here, which is 3, and a level change here, which is 4. So there's actually 4 level change events between detents. So this most recent interrupt service routine counts 4, 1 count per each level change event. It's a little bit better, and it's a little bit less sensitive to mechanical issues and other things that I found creep in to these Bourne's rotary encoders. So that's what's going on with that. Let's take a look at the interrupt service routines. I've got some shell code here, and let's just take a quick peek at that. This is all packed into the zip file, and these are the interrupt vectors you'll need to use for the pragmas if you're going to go with these interrupt service routines, and they'll go ahead and make an entry in the interrupt vector table so that these small routines get executed when the physical interrupt pins get triggered. So the first set here is what's being used most recently, and all it does is it captures each level change event and winds up generating a count 0, 4, 8, 12, 16, and so forth. This is the old interrupt service routine, and this one works, but it generates only a single count between detents, and I found this one works better. So this is out there. You can play with it and include it in your projects if you'd like. So let's go back to what's in the zip file. Let me just talk a little bit about this init routine. I kind of like knowing what code does, and this is part of the Arduino core functions, and I went ahead and found it. It's a little tricky to find, and I included it in here. Here's the source code for it, and you can go through this and you can actually see what it's doing. It's setting up some of the registers, and this SBI stands for set bit. So you've got a register here, and you've got a particular bit that's being set to accomplish something. So if you're going to use this in your code, change the name here, put a 1 in here, and then just include this in your code so that you don't have a redefine error when you do a link, because this routine lives in the core library. So you can do that, but that's there if you want to go ahead and do that. So let me go back here and let's take a look at the Nano Header. This is a bit of a deep dive, and before we go there, let's take a look at this diagram. What I did on the Nano board, the Nano V3, is I just labeled this as you see in the photo here, just like a DIP package with the pin 1 at the upper left, pin 15, pin 16, pin 30. So regarding the header file, the nano.h header file that I put together, all the pin numbers are like this. So if you're looking for D2 on the silk screen, and I include that in my comments, pretty well commented, D2 would be 1, 2, 3, 4, 5. So this would be called out as pin 5, pin 6, pin 7, and so forth. Some of these pins are not going to be included, like for example pin 3, pin 4. These are pins that you're not really going to be using. And then over here as well, this VIN pin is not going to be an I/O pin, so you're not going to use that. But all the pins that are usable for inputs and outputs and analog inputs can all be accessed from that header file. So that's out there. So let's go back into the files here and let's take a look at this. Here's the deep dive on the nano.h header file, and the explanation for all the pins are up here in the comments, and there's some shell code here for how to set up interrupts. You can make those whatever you want. And let's go to the interrupts. These are 1, 2, 3, 4, 5, 6. These are 12 macros that are very easy to use, and they handle programming and configuring your int0 and int1. And it's pretty self-explanatory. You can turn these interrupts on and off, and be aware that you've got to have global interrupts turned on before any of these will work. But these macros here turn on these specific interrupts. And then you've got the configurations, triggering on a low level, triggering on a change of level, triggering on a falling edge, triggering on a rising edge. And they're just duplicates. They work the same way. So that's that, and that's all in there. It makes it very easy. And this deals with the pull-up resistors. There's the master control register, microprocessor control register, microprocessor control unit control register, whatever you want to call this. Basically disables all the pull-up resistors globally, or enables the ability to select individual pull-up resistors. And I'll come back to that in a minute, but let's go into some of the basics. These are your macros to configure any one of the available pins as a digital output, hence the DO. These are the macros that allow any of those pins to be configured as a digital input. All you have to do is just use the macro with a semicolon in your code, and it's done. And these macros down here are what would be used to read the value of a pin as a digital input. So you can go ahead and read what, 0, 1, what's going on with a pin. And it is used for the interrupt service routines, and you can actually read outputs and see where they are. And this collection of routines is for writing a value to a digital output. So you can go high, you can go low, or you can toggle it. Every time you execute this, whatever it is, it'll toggle to the other state. And these are all the pins that are available that you can use. And that pretty much is it. I have some extra functions forthcoming. I've got an EEPROM write and read. We'll get into that a little bit later, but that's kind of in anticipation of that. So that's pretty much how this file works. So coming back to the pull-up resistors, it is explained in here, and it's right here. And what happens with the pull-up resistors is if you configure a pin as a digital input, you're going to get a weak pull-up, which is like in the 50k ohm range, so it's very weak. So it just keeps the pin high. And what you do is, obviously you have to turn on the global pull-up resistor function, and as the pin is configured as a digital input, just write a 1 to it, and that'll turn its pull-up resistor on, and you can go back and write a 0 to it, and that will turn off the pull-up resistor. Or if that pin is configured as a digital output, that will cancel the pull-up resistor immediately. So that's how you handle your pull-ups, and that's that. So let me go into the LCD functions. There's a header file that's associated with that, and this is your New Haven 4-row by 20 character display size. These are the macros for it. This is the SPI bit bang frequency. I recommend you leave that at 10. And these 9 macros here are really important. These are what control the signals that go out to the SPI on the LCD unit. So there are 3 signals. It's a write-only device. There's slave select, there's serial clock, and there's master out, slave in. So it's pretty likely that you'll need to change these pins so they match your particular application. I use 19, 20, and 21 for these signals. So just be aware that those are going to have to be tweaked so they match the wiring. These are macros here that work in conjunction with the LCD functions, and they're indicated here in the comments which goes with what. So the functions are on page 7 in the specifications manual that goes with the New Haven LCD, but these are all the functions that I've written, and they allow you to do pretty much anything you'd want to do with the LCD. The most important one is this SPI Send, which is the bit bang. The reason for that is the LCD, the microprocessor on the LCD tops out at a serial clock of 100 kilohertz. And unfortunately, the Nano board running at 16 megahertz, when you divide it down, the slowest serial clock you can get is 125 kilohertz. So a little problem with that. So I wrote this bit bang routine, which I checked with my scope, and it runs at about 25 kilohertz. That's about the equivalent serial clock. And all the videos that you see with the LCD run from this SPI bit bang send function at 25 kilohertz. The display updates pretty much instantly, so there's no perceivable delays or problems. So this should work out pretty well. It's been tested reasonably well too. So we've got the functions here. They're explained, and they're also shown in the sample video, so I won't really spend a lot of time with these, but they're all here. The ones that are sort of what I call enhanced are these 2 at the bottom, and these have been written as convenience functions. This one allows you to position a string and send it to a specific row and column. It's very handy. You'll see how that's used in my example. And this one is a clear line or clear row. It just writes blanks out to a given row. So these functions are not native to the LCD microprocessor capability, but they're built on these functions here. So I've included those. So those are handy. So getting into the source code for the LCD functions, that's in this file here, and these are all the functions right here. And again, the most important one is this SPI Send. Get that one working first. That's your bit bang routine that simulates the SPI signals that the LCD needs. So these are all the functions. So that's in this C source file, LCD_basic, and the program that is running for the test functions sample video that's in the thread, that program is here. So this shows how some of these functions are used. And here's the LCD send string, which is just sending this string to row 1, column 1. It's very simple. It's not complicated. So you look through this, and this is the whole ball of wax here. One comment on the video, my camera obviously tries to do an automatic exposure adjust. So when I do a backlight and I back the backlighting down from 8, 7, 6, 5, 4, 3, 2, and 1 is off, the camera tries to change its exposure, so it kind of looks like nothing's happening. But if you run this sample and actually see the backlight in person, it'll work actually quite well. So that's it on the test program. That's again all in the zip file. We took a look at the interrupt service routine example, and we took a look at that int.c just in case you're curious and you want to see what's going on. So here's the whole ball of wax. It's in the zip file. It's out there in the thread. Again, the link to this is in the description for this video. So that's kind of it. So hopefully this video is helpful, and if you have any questions, you can email me or you can put things in the comments and I'll get back to you. So that's it. So have a nice day. Thanks for watching.